we are reading the properties of group and we identify some more groups. So, group theory. See, already we have seen that if A is one set, with n numbers of elements and one operations dot, so that my A dot is form a group, then these elements with the operations can be represented by a n by n matrix. Now, and also we have seen that no two rows or no two columns that are in two elements in a row or no two elements in a column are identical. We have proved that thing. Now, say we see if is n equal to 2, if n equal to 2, that means my set has two elements and let these elements are A and B, these are the two element sets, and we take the operation is dot and A dot form a such that A dot form a group. Now, if this will be a 2 by 2 matrix and we see that what will be the elements of the matrix. So, we represent like this. Now, see A dot A, that means I need, since it is a group, it has some identity element, and since it has two elements only, so one must be the identity element. So, let A is the identity element. A is the identity element. So, we can write A dot A is A only. Now, since A is identity element, so A dot B is B only. Now, similarly, B dot A is B only, since it is a commutative, that property also we have seen. And now, if it is B dot B, then it is B only. B dot B is the A, because otherwise B will be the identity, since we have already assumed that A is the identity element. Now, if I continue this thing for n equal to 3, so if it is n equal to 3 and my set is A, B, C, the 3 element set, operation is as usual dot we see, and A dot is the group and A is the identity element. Then if I give, then I have 3 elements, I give dot A, B, C. See A dot A, since it is identity A dot B, B, since A is the identity, it is C. Now, B dot A, it is B only. Now, B dot B, I write it is C, and B dot C, it is A, and C dot A again C, then C dot B, already B dot C is A. So, C dot B is A and C dot C is B. So, I get that the first row is ABC, then BCA and then CAB. So, with only 3 elements, but no 2 row, and in the row no 2 elements in the row or column are equal. So, it holds the properties we have read. Okay. Now, we read one examples, that see one example of group. So, let Zn equal to 0, 1, 2 up to n minus 1, that means there are n elements set. Zn is an n element set. And we denote this operation is a modulo operation, is a mod operation of additive modulo n, and then we will see whether it forms a this set, whether we check whether Zn with modulo operation, whether this forms a group or not. Okay. Let we consider or we assume n equal to 7. That means my Zn is 0, 1, 2, 3, 4, 5, 6. Since I will be taking modulo 7, that my operation is modulo 7. If we remember that modulo 7 means the number if we divide by 7, we will be taking the remainder, it will give the. So, if we divide by 7, the remainder can be from 0 to 6, and that is my set. So, if I draw the group operation or the effect of this modulo operation on the set Zn in matrix notation, just now what we have read. So, it will be the give zero, 1, 2, this is my modulo 7, because my set is up to 6, there is up to 6 elements. Now, if I because it is additive modulo mod operation, this is additive modulo n, additive modulo n, that means every time we will add and we will be dividing by 7 and taking the remainder. That means 0 plus 0 divided by 7, obviously it will be 0, then 0 plus 1. So, since 0 is my identity element, so I will be getting 1, 2, 3, 4, 5, 6, because all are less than 7. Now, since it is for 1 plus 0, this becomes 1, because 1 divided by 7 remainder is my 1 modulo 7 is 1, 2, then this becomes 3, 4, 5, 6. Now, 6 plus 1 is 7, and if I 7 modulo 7, if I take, that becomes 0 because remainder 0. So, I give here 0. Now, 2 plus 0 is 2, 3, 4, 5, 6. Now, again 5 plus 2 7, 7 modulo 7 becomes 0. Now, 6 plus 2 8, 8 modulo 7 becomes 1. Similarly, we can fill up 3, 4, 5, 6, again 7 becomes 0, 8 becomes 1, 9 becomes 2. Then 4, 5, 6, 7 becomes 0, 8 becomes 1, 2, this becomes 3. 5, 6, then 0, 1, 2, 3, 4. Now, this 6 and now it becomes 4, 6, 6, 12, 12 modulo 7 is 5. Now, we see once we got the effects or the operations of modulo 7 of the set Zn, then we see that if I study, then my matrix elements are only 0 to 6. So, first thing is that it holds the closure property. So, the closure property holds because my matrix elements are also lies between 0 to 6. Now, associative, since it is addition. So, if I take any we can take A is 4, 5, 6, that means A equal to 4, B is 5 and C is 6. So, I can take 4, 6, this is equal to 5, 6, 11. So, this becomes 11 modulo 7, 11 modulo 7 is 4 and 4 modulo 4 8. So, 8 modulo 7 is 1. Now, if I take 4 modulo 5, then modulo 6. So, 4, 5, this becomes 9 modulo 7 is 2, 2 modulo 6, 2 plus 6 modulo 7, that means 8 modulo 7, that is also 1. So, I have this is equal. So, it forms a associative property. So, it holds associative property. Now, the 3 is identity element. Identity, since it is additive modulo 7. So, identity exists and equal to 0, and inverse, this is that since it is additive. So, inverse is some minus A, since it is additive modulo 0. So, we can take that, if I take, we will be getting some A and minus A, this is equal to the identity element E. That means, A minus A 0, this will be my, and it is my identity equal to 0. So, inverse exists. So, it forms a group. So, it is a group. Answer is, so my answer is it is a group. So, additive modulo 7 or additive, now we can generalize that additive modulo n on the set Z n 0 1 to n minus 1 in element, that it will be it always forms a group. Now, we see another property of group. Already we have defined the sub semi group or sub monoid, and similarly we can define the subgroup. So, we define similar way we can define the subgroup. If we remember that if T is a subset of S, where say S dot is a group and T is closed, under the operation dot, T satisfies the associative property or and now the two property, that identity and the inverse element, that and the if E is the identity element of S, since it is a group, so it has some identity element, then E belongs to E belongs to T. Okay. Then if E belongs to T, and about the inverse, that there exists an inverse element A dash for all A belongs to T, such that A dash also belongs to T. Then T is a subgroup of S. T is a subgroup of S. Now, we read two properties we actually defined, and then we will give a theorem on this, that it is called the Cosets and the Lagrange's theorem on this. So, first we define Cosets. So, let T be an algebraic systems and dot is the one is a binary operation. Now, let A belongs to T, and H is a subset of T. Then the left coset of H is defined as, and always the coset is defined with respect to one element of T, the original set, here it is T. So, left coset of H in respect to A is A dot H. A is A dot H. That is, I can write A dot, since H is a subset. So, I can write A dot H equal to all the elements A dot x, where that all x belongs to, for all x belongs to H, and dot is the binary operation that we have chosen. Now, similarly, the right coset of H in respect to A is H dot A, that is, we can write H dot A, again since for all x element A and x belongs to H. So, this is the two things, that left coset, the left coset and the right coset of H, where H is a subset of T. Now, we give a property on this, one property we write on cosets. So, let A dot H and B dot H are say two left cosets of H. Or sometimes we call cosets of H. Then either A dot H and B dot H are distinct, or they are identical. And we can easily prove this property from earlier matrix representation, and that what we have identified some property that no two elements in the row or in the column, they are equal. And another thing we always remember, that since it is a set, so these are distinct element, and so if they are, either they will be distinct or they will be identical if they are not. Now, we read the the Lagrange's theorem. Now, Lagrange's theorem tells about the property of the order of a group. If we remember the order, we have defined that the size of a group, and the group must be finite, otherwise there is no concept of a size. So, we can write that any group any group of prime order So, it tells about the order, and any group of prime order is cyclic, and any element other than the identity element is a generator of that group. Since it is a cyclic group, so it has some generator, and other than identity element, every element, any element can be the generator. That means that if we take the power of that particular element, it will generate or it will produce the other elements. So, this is very important when we will study some algebraic systems. Another thing is always that this is it also forms a abelian group, that it also follows the commutativity, that means it is always an abelian group. So, you can write that any T dot is a group and A not equal to the identity, then and A belongs to T, then A is the generator of the group. So, we have read the definition of group and some properties and some theorems related to the order of the group. Now, since we have started our discussion with the algebraic structure and we have defined like that we have a set and operation defined on it, and if we remember then that some relations on this function, that gives you the algebraic structure. Algebraic system is a set with the operation, and then when in addition if we consider some relations on this, then it will give a algebraic structure. So, now when we define the algebraic structures, so the relation between the one algebraic system to another algebraic system is very important, and that we define with something called the homomorphism and some other variety of homomorphisms. So, we define mainly the two, there are other varieties also, the homomorphism and another important is the isomorphism. Homomorphism and isomorphism. We will show that if two algebraic systems are isomorphic, then they are structurally similar. So, homomorphism and isomorphism we read, we give the definition that since it gives a relation between two algebraic systems. So, I consider two algebraic system x dot and say y star. These are be two algebraic system. And dot and star are the two operations. Now, a function if from one algebraic system x to y is known or is called homomorphism, right? We can write x is for x dot to y star if for some x1 x2 belongs to x, we can write that the property is that f of x1 dot x2, the operations defined on x, this is equal to f of x1 operations defined on y and f of x2. So, the function is this, then we call that these two are homomorphism between x and y. And here only we can tell, since it is a function, so we know that if the function is onto, then the term is epimorphism, then we call epimorphism. If the function is 1 to 1, then it is monomorphism. And if the function is one to one and onto and 1 to 1, then it is isomorphism. So, now it is clear that if it is onto and 1 to 1, that means they are structurally two algebraic systems, they are same or they are structurally similar. Then we can tell that they are structurally similar algebraic systems and they are isomorphic to each other. We can take or we write in a different way, that if we write that take one example, that if A 1 S O C and 1 A dash S dash O dash C dash, these are two algebraic systems. Then just with this thing we can write, we graphically we can tell that if I take this is S, this is my O, so it gives to S dash, okay, sorry, S cross S to S and if I give say some homomorphic thing, homomorphism, say S dash, so this becomes S dash by S dash, this is something O dash, so this becomes S dash and again this gives a H. So, that means here H is I can write H is S to S dash and H some two elements if I consider A dot B is H A dash H B dash, the way we have defined. And if I consider some constant, then that constant is H C equal to C dash. So, this is the general definition of homomorphism and it will graphically it will show in this nature. So, the way we started that actually the study of algebraic structures. So, in this lecture we have read some algebraic systems like semi group, monoid group and then the how that from the relation between or the how from one algebraic system to another algebraic system we can get by applying some function, and based on that the nature of the function, whether it is onto 1 to 1 or onto and 1 to 1, we get the whether the homomorphism that becomes the epimorphism or monomorphism or the isomorphism. So, mainly our focus is on the isomorphic thing, whether two algebraic systems are structurally similar or not, that means whether they are isomorphic or not. So, with this we complete this lecture here, and in the next lecture we will again study some more algebraic systems which have practical utility and they are used in the different streams of computer science and mathematics.